All right, great. Hey, good morning, everybody. Thanks for joining us today on the session about Don't Be Salty, Best Practices to Keep Waterways Fresh. And with that out of the way, I'm going to introduce our panel of speakers. You all are in for a real treat today. Not only are all three of our speakers top-notch presenters, but they're doing leading-edge research on a bunch of things, including freshwater salinization. I'm sure you're going to learn something really interesting today. So our panel is three people. First speaker is going to be Sujay Kaushal, who's a professor in the Department of Geology at the University of Maryland College Park. His expertise is in the areas of water quality, biogeochemistry, and hydrology. Sujay has taught well over 2,000 students about water resources over 20 years with the University of Maryland. And his research team was the first to document freshwater salinization as a major concern for drinking water and aquatic life in the eastern US, and identify connections between salinization and increasing urbanization we've seen in the Metro Washington region and elsewhere. He now works closely with students, collaborators, agencies like my own, the Council of Governments, on understanding the diverse causes and consequences of salinization and ways to manage it. Our second presenter is going to be Dr. Stan Grant. He's a professor in the Department of Civil Engineering, Environmental Engineering at Virginia Tech. He also serves as director of the Occoquan Watershed Monitoring Laboratory in Northern Virginia. And he's the principal investigator of a $3.6 million National Science Foundation Growing Convergence Research Project to catalyze stakeholder-driven solutions to salinization of inland freshwaters. He and his colleagues and students have published 100 articles in top journals, and many of his former PhD and postdoc students are now themselves professors at research universities around the country. Stan received his BS with distinction in geology from Stanford University. He has an MS and PhD in environmental engineering science from the California Institute of Technology, sorry. And our last presenter is going to be John Jastram. He's a hydrologist who serves in the studies section chief as a program development specialist for the USGS, U.S. Geological Survey, in their Virginia and West Virginia Water Science Center in Richmond, Virginia. John has spent much of his career monitoring and studying water quality issues in urban areas across Virginia. In his current role, John leads a team of scientists focused on water resources issues ranging from groundwater quality and availability to land subsidence, surface water quality, as well as leading efforts to expand partnerships with federal, state, and local agencies, tribes, and other organizations. John has a BS in environmental analysis and planning from Frostburg State University in Maryland, and an MS in environmental science and engineering from Virginia Tech. So with that, I'm going to turn it over to you, Sujay. Take it away.
Sure. Thanks a lot, Steve. And before we begin, we'd like to thank Washington Metropolitan Council of Governments for bringing us together to talk about this research. And thanks for inviting us. So next slide. So what I'd like to talk about is that we have a partnership, and it's basically with different organizations, Virginia Tech, USGS. It's been a highlight of my job so far to work with these guys because we've learned a lot about salinization issues. Next, I think there's some graphics. Yeah, go ahead, keep going. Okay, the USGS provides the backbone in terms of monitoring for salinization in our region because they basically operate the long-term gauges where we can look at long-term trends in salinity. And so they take the pulse of the watershed, so to speak. And then Stan, he works on modeling issues. He's a very innovative engineer and looking at potential solutions and what could happen in the future. And then our work in this project is basically looking at field and lab experiments to look at the mechanisms behind what's going on with the salt and what are the potential impacts in the future. So we're basically synthesizing knowledge to understand and manage freshwater salinization syndrome, which I'll explain that in a little while, in the metropolitan region. So we're going to talk about the spread of freshwater salinization syndrome, how it mobilizes chemical cocktails, and then what we can do to manage it. Okay, so next slide. So this story begins in Baltimore, in the Baltimore region. About 20 years ago, we published a paper looking at increasing chloride trends in the Baltimore drinking water supply and in streams and rivers around the northeastern United States. And we predicted within this 100 years that it would affect the potability of drinking water. And what we didn't know at the time, but what we know now is that it wasn't just chloride. And when we think of salt, we think of sodium and chloride, but it was all these other ions that were also increasing in the water as well. And we also didn't know the secondary impacts of these salts. For example, in Flint, Michigan, some of you are familiar with the Flint water crisis. What happened was they switched the water source to the Flint River, which was enriched in chlorides, and that water was more corrosive, and that corrosive water leached out the lead from the service lines, and they didn't add enough corrosion inhibitor to counteract those effects. So this issue of salinization is becoming more of an issue in terms of not only its direct effects on potable drinking water, but also its indirect effects and the chemicals that are associated with salts. Next slide. And this issue is going to increase in the future. These are increasing salt trends for the United States, salt production and use. And you can see that we use salt for a variety of different things. We use salt in terms of the biggest use is de-icing roads. And we also use salt as food additives. It's also in wastewater that's reflected from our use of salts in domestic households, and Stan will probably talk about that. We actually worked on a global salt cycle, believe it or not. So when I teach, like Steve was talking about, I'm a teacher also. And so when we teach class, we talk about the rock cycle, the water cycle, and we also have a salt cycle now, a global salt cycle that's been perturbed and unbalanced. And that's going to lead to more salinization issues in the future. Next slide. So I noticed on the call that we have some friendly names from ICPRB and Maryland Department of the Environment in our region. And so what brought us together was the Potomac River. So we've done work looking at salinization at national, global, and local scales. On your left is like a heat map of salinization, and the red areas are where you have decadal or over the last 40, 50 years, increasing trends in electrical conductivity, which is an indicator of salinization. And you can see that, you know, the Western United States is red. And then where we live in the Mid-Atlantic in Region 3, that area is orange and red. It's like a canary in the coal mine, basically. It's got increasing trends. And you can see some of those trends if you look to the upper right-hand panel. And the purple circle is the Potomac River, which is in our region. It provides drinking water, probably about 2/3 of the drinking water in our region. And it's got an increasing sodium trend, okay? And so sodium and can be of issues from hypertension with people on sodium-restricted diets. In fact, there were concerns about sodium in the Philadelphia drinking water supply. There's a recent paper by Cruz et al. That was published about that. And if you look on the lower right-hand panel, what you'll see is increasing chloride concentrations around the world with some U.S. rivers. And this is not only reflects the increasing sodium trends that we see, but the chloride trends are important from the corrosivity standpoint and the leaching of metals from pipes. So in the Washington metropolitan region, people were concerned about this, and they approached the Council of Governments on research needs. And so our team was put together to look at that. I'm just going to talk a little bit about some of the results that we've found. There's a lot. But one of the things that we found that we want to stress is that the salt mobilizes chemical cocktails or harmful mixtures of elements, and it can be nutrients, metals, and even radium and radionuclides. Move to the next slide, please. So we and other researchers have documented this movement of these chemical cocktails in groundwater, streams, and rivers. But one of the places that you would not think to look that could be important are stormwater management features. We spend billions of dollars in the United States on stormwater management with the hopes of reducing peak flows and also purifying the water as water moves through these stormwater management features. So salt can actually degrade or counteract our efforts with stormwater management. Stormwater management is very effective. It can be effective at retaining nitrogen, phosphorus, and different metals. And we've reviewed that literature because a lot of our work is on restoration as well. But the salt can actually cause dispersion of the soils and break down the soils, and then release contaminants that are stored on the soils through a process called ion exchange. Next slide. So if we add salt, when we add salt to these stormwater management features, the area shown, these are experiments shown on the left-hand side. That lightly shaded area in gray shows the amount of salt that's added that's retained in the soils of the stormwater management features. We can get 30 to 40% of the sodium that's added that's retained in the stormwater management feature. And we actually did a salt budget for the United States. Actually, Stan encouraged us to do this. And we found 30 to 40% of the salt that was added at the national level was actually retained in soils and groundwater in the United States. So these little stormwater management features are a microcosm of what's happening in the continental United States, where you have this retention of salt. Now, the thing is that the salt is retained, but on the left-hand side, when you have the salt that's being retained in the soil through ion exchange, it actually displaces other metals and harmful chemicals. Like on your left-hand side, there's copper. There's things that we have regulations for, some metals that are mobilized: copper, zinc, cadmium, and also other work has shown radium is an issue. I was just at a talk at the Delaware Geological Survey where they're looking at radium transport in groundwater from salt, and others have documented that as well. So the secondary mobilization is a big issue. Okay, next slide. And if you monitor during snow events, it's hard enough to monitor as it is, and monitoring during rainstorms can be is hard. But if we monitor during snow events and road salt events, we'll see that there can be acidification that happens because the sodium ions are positively charged and they displace hydrogen ions into the water and cause a temporary acidification reaction. There can be mobilization of nitrogen. There can be release of ions and different metals, and also reactive organic matter that all changes in response to those salt additions. Okay, next slide. So not only are we working with Stan and John, which has been a gift, and I'm not just saying that because they're here, but it really has been, I've really learned a lot from them. But we've also worked with the EPA in Region 3. So after all the years, we have students that work for EPA, like Steve Homan, who's on your left-hand side. He works at EPA Region 3, and he got a fellowship to work with our lab, a ROAR fellowship. And then Sydney Shelton, who's a PhD student, who's been working on an EPA ORISE fellowship, and then working with us as well. And Paul Meyer and Virginia Basilotti. So, some of that work is outreach work where they're actually building a story map to tell the freshwater salinization story and how it mobilizes these harmful chemical cocktails in this story map format that will be available to the public. Next slide. I want to leave you with some hope, and so some of the work that we found is that conservation and restoration can reduce the salt, basically help take up the salt and reduce it. When we sample along a stream longitudinally, moving from the top to the bottom of the watershed, if the stream flows through parks and conservation areas, then you can get a reduction in the salt because you cut off the inputs of salt to the system, and also because the sediment or the mud and the sediments can retain the salt. And so we've demonstrated that, or we've looked into that and observed it in a variety of different streams in Bull Run, which is where Stan lives. And he'll talk about that watershed where it flows through a forest conservation area, restoration sites, and then Rock Creek. And we have a star student of ours who works for John now, John Jastram at USGS, who wrote a paper about this as well. Okay, next slide. And if you would have asked me 20 years ago, if conservation, like little urban forests and that sort of thing, made a difference around streams and improving water quality, I would have said, no, probably not. It's overwhelmed by urbanization. Most of our monitoring is done at one site over time. And we started or we haven't started, we've been doing this for the last 20 years probably, but we've learned the full potential of it, sampling up and down the stream to see how the water quality changes with any surrounding changes in restoration or conservation. And we get different results. We see that when you go through these areas, that the amount of forest area can be related to declines in all kinds of contaminants, just like people have looked at impervious surface cover and shown that it's positively related. So conservation is worth, like Ben Franklin said in Philadelphia, an ounce of prevention is worth a pound of cure. Next slide. And, just to recap, salinization syndrome is spreading. Salt mobilizes these harmful chemical cocktails. Salt can be managed through nature-based solutions and engineering solutions. And speaking of engineering, our next speaker is Stan Grant, a very innovative engineer working on this issue with drinking water. Thanks.
Thank you, Sujay, and what a great way to tee up the presentation. As Sujay mentioned, I'm a professor at Virginia Tech and director of the Occoquan Watershed Monitoring Lab here in Northern Virginia. And I came to this area in 2018 from Southern California, so a bit of a different climate. And I could never have envisioned working with the likes of the USGS and Sujay's group at University of Maryland, really a dream. And that all started when I arrived as director of the lab, and I went to the local water utility here, Fairfax Water, and I asked the general manager what was the one thing that really keeps him up at night in terms of the long-term viability and sustainability of this water supply for 1 million people, and he said salt in a word, and that kind of gave me an excuse to reach out to Sujay, and we've had a really productive and wonderful collaboration, I think, since, including with the USGS and MWCOG and many other stakeholders in the region. And one of the kind of engines that's been fueling that collaboration is the National Science Foundation Growing Convergence Research, or GCR program. If you're not familiar with the GCR program, it's worth looking up. It's one of NSF's top 10 ideas, and the concept is basically bringing together a divergent set of viewpoints to try to tackle societal grand challenge. So in our case, we're basically looking at the science, policy, stakeholder engagement, and engineering aspects of salinization, and through convergence research, trying to formulate solutions that will sustain our water supplies and ecosystems going into the future. And just on the left there, you can see some of the institutions that are involved, and then a picture of Sujay and his students out on a field trip that we had a couple of years ago. Next slide. One of the things that we did in this project early on is we brought the stakeholders together, a really large group of stakeholders, and kind of asked them to brainstorm around, what we could accomplish if we were fabulously successful with this 5-year project. What would the endpoint be? And Carl Berger, in particular at MWCOG, helped us formulate this particular vision, which I really like. What you saw, Sujay presenting a lot of upward trends in terms of ion concentrations there on the vertical axis over time on the horizontal axis. And so we may be in the present situation kind of on the left there, maybe at or near serious thresholds that we might worry about for drinking water taste, for example, or ecological impacts, or even human health impacts. And that's not to say some of our water bodies are already there, but one of the concerns is if we're seeing these upward trends under business as usual, how quickly are we going to pass through all of those thresholds if we haven't already? And then how will climate change and population growth within our watersheds influence that trajectory over time? So that was one of the really significant questions that they were hoping that we could try to tackle in this system. And then the other piece of that is, those trends are composed of something, they're driven by something. And so how does the relative contribution of different potential sources contribute to the trends in terms of, for example, salts added during water and wastewater treatment, because we really are dealing with one water systems now. What's happening at the household level and industrial discharges that could influence these trends. De-icers and anti-icers are obvious contributors as well. And there may even be legacy pollution or natural sources out there as well. So these are kind of some of the big kind of almost science questions, like what's happening going out into the future, what's driving these trends, and how is climate change and population growth going to affect those trends. Next slide. And maybe the engineering aspect of this is then, well, what can we do in terms of interventions to, slow the trends or maybe even reverse them? That would be ideal in terms of, for example, best management practices, regulatory action, or what we call collective action rules, if it's essentially a voluntary effort, public education and social marketing, de-icer alternatives, and so on. So this is kind of the vision that I want to leave you with, and then I'm going to give you some examples of our work in the Occoquan watershed system. And I'm not sure we made it all the way here, but I think we made a lot of progress. Next slide. So let me tell you a little bit about the Occoquan Reservoir in case you've never heard of it before. We are located in Northern Virginia. It's a drinking water source for up to 1 million people in Fairfax County and surrounding communities. So many of you may actually drink the water from this reservoir. It's one of the first and largest deliberate indirect potable reuse projects for surface water augmentation in the country. That's a mouthful. But what that means is that the reservoir received inflow from two major watersheds, the Bull Run watershed and the Occoquan River watershed. It receives some inflow from around the reservoir itself, which is ungauged. In other words, we don't measure the flow in. And then it also receives a substantial input from a water reclamation facility that is discharging treated wastewater, and that's the Upper Occoquan Service Authority, or UOSA. And I'll be showing you slides of UOSA kind of position in the system shortly. And the picture on the right is basically the dam, basically overflow over the dam. Here's kind of a block diagram showing how the system is configured, and those numbers on each of the arrows correspond to the million gallons per day on an annual average discharge from each of the major sources. So like I said, there's two major watersheds, Bull Run and the Occoquan River. You can see the Occoquan River is contributing about 300 MGD, so it's the larger source of water. It's the bigger watershed. The water reclamation facility, UOSA, contributes about 33 MGD on annual average. And then collectively, the water from those three sources, UOSA, Bull Run, and Occoquan River, flow into the Occoquan Reservoir, which mixes with ungauged water. Some of that, about 60 MGD, is pulled out by Fairfax Water and treated and then distributed through water distribution systems. And then the rest flows to the Potomac River. Next slide. So I'm going to be using that diagram, that block diagram, to kind of walk you through what we've learned about those relative contributions to the different sources and how they're changing over time. So let's start at the sort of back end of the system first. So this is the finished drinking water that's flowing out of Fairfax Water from the Occoquan River after treatment. And what you're showing is basically similar to a lot of the trends that Sujay showed a minute ago. In this case, we're looking at sodium ion concentration on the vertical axis and time over the last 40 or so years. And you can see that there's an upward trend in both kind of the average as well as some of the extremes that we're seeing. And just to kind of benchmark this, 30 milligrams per liter is roughly a taste threshold for sodium, and 20 is EPA's guidance for extreme low sodium diets. And so you can see we've really surpassed the 20 and often the 30 milligrams per liter thresholds quite a while ago. Next slide. And then if you look across the water treatment plant, one of the surprises was that approximately 30% of the sodium on an annual average, again, is added by the Griffith water treatment plant itself. And that was a surprise because we hadn't seen that kind of addition at the other water treatment plant that Fairfax Water runs. And I think it's a rather unusual circumstance. And we've been digging into it, and it turns out that that addition is coming primarily from caustic or sodium hydroxide that is being added for pH control, and specifically to comply with lead and copper rules, and keeping the pH well above 7. And the other thing that's really interesting is that pH adjustment, about 50% of it is coming from the acidity in the reservoir itself, which peaks in the summer when the reservoir is stratified. And so there's a very strong coupling between the ecology of the reservoir, the biogeochemistry of the reservoir, what's happening upstream in terms of inputs, and then what Fairfax water has to do in terms of pH adjustment, and then ultimately sodium addition. Next slide. If we look at where that sodium, coming from the Occoquan Reservoir, where in turn it's coming from, we can divide that contribution into these three major sources: the Water Reclamation Facility, Bull Run, and the Occoquan River. And on an annual average basis, this is the breakdown. Remember, Occoquan River was the larger source of flow. It's the minority partner here in terms of sodium because it's a less developed watershed. As Sujay was saying, there's a very strong relationship between development and sodium inputs. The reclaimed water is also sort of an outsized source of sodium here at about 18%. It represents much less of the flow on an annual average basis. And then Bull Run is kind of the biggest slice of the pie at 44%. Next slide. But what's misleading a little bit about that annual average value is that, as you well know, there are extreme temporal variability in flow in this region due to rainfall. And so what we're plotting here is the instantaneous sodium loading into the reservoir from our three major sources on the left: Bull Run, the Occoquan River, and reclaimed water. So those vertices represent essentially 100% of the load measured on a given day that would be coming from one of those three sources or a combination of the sources. And what you see is that that gray dot there is our average value. So it kind of plots toward the bottom. But on a daily basis, the average is almost never experienced. In fact, the ternary diagram here is completely filled out, which basically means that day to day, there's enormous variability in the contribution of these three different sources to sodium input to the reservoir. We've colored the points by the log of the flow into the reservoir. So red would be really dry days, and then blue would be really wet days. And not surprisingly, during really dry days, up to 100% of the sodium can be coming from the reclaimed water. During wet days and big rain events, most of that sodium is actually coming from the two watersheds. Next slide. And then that I'm going to kind of walk through, well, where is the sodium coming from kind of upstream in these different sources. And I'm going to start with the reclaimed water. So where is sodium in the reclaimed water coming from? Well, we worked with UOSA to kind of break down the annual average inputs to its system and discharge from there to Bull Run in the pie chart here. And you can see that wastewater treatment at UOSA adds about 4%. Water treatment adds about 4%. Of course, this water is, coming from another water treatment plant, and that's the Corvallis water treatment plant, which pulls from the Potomac River. And so they add some chemicals during that process. And so they're adding about 4%. It's about even inputs from the wastewater treatment and the water treatment. We estimate human excretion is adding about 14%. There's an industrial discharge from Micron, chip manufacturing firm, which adds about 14%. But then if you compare all of those known sources to what we measured coming out of the system, that leaves a whopping 64%, which we couldn't immediately account for. Next slide. So to get at the 64%, we basically sampled along the flow path from rainwater to the Potomac River, which is the source water, through the Corvallis water treatment plant, finished drinking water, and then the sanitary flow. And what we're showing in the bar charts in the bottom left there is the sodium or chloride concentration along that flow path. And what you basically see is that, rainwater has very low concentrations. The Potomac has substantially higher. There's some addition as that water flows through the drinking water treatment plant. But then there's a whopping increase as that finished drinking water flows through homes and businesses and then eventually into the sanitary sewer system. So there's a really big jump in that sodium contribution coming from homes and businesses within the sewer shed. And I should point out that this particular sewer shed did not include microns, so it's more a residential sewer shed that we were sampling. The other thing we noticed is that the sodium to chloride molar ratio, which is on the top graph there, goes from a little bit depleted in sodium in the Potomac River and the finished drinking water to being really enriched in sodium in the sanitary flow, which gives us a hint as to where all of this salt might be coming from. Next slide. So there are some great studies out there, and this one in particular from CSIRO in Australia, where they had a model house and monitored ions coming out of various waste streams from the house. They were really particularly interested in gray water reuse here. So this was part of the Millennium Drought sort of response. And what they found, if you look at the bottom row there, the molar sodium to chloride ratio, that washing machines in particular generate very sodium enriched sort of salt output. And in fact, we know where those are coming from because surfactants are salts of sodium very frequently. And sodium sulfate is used as a bulking agent in powder detergents. And so we've done follow-up studies pulling detergents and various household products off the shelf in grocery stores. And we're basically seeing a lot of variation across these products, which is great in a way because it suggests that maybe social marketing could make a huge difference here. Next slide. Where is the sodium in the watershed coming from? Well, again, we've got two major watersheds, Bull Run, which is a bit smaller, and Occoquan River watershed there in kind of the tan, a bit bigger. Next slide. And we have, as part of the Occoquan Watershed Monitoring Lab that I direct, we've been sampling in the tributaries to those two major watersheds or streams for the last almost 40, 50 years. And here's some sodium data going back at least 20 to 30 years from those different stations, arrayed by percent imperviousness of the watershed draining to those stations. And not surprisingly, as Sujay mentioned, as the imperviousness increases, you generally see an increase in the median sodium concentration and also the extreme values. Look at the magnitude of the vertical axis there, going up to 400 milligrams per liter. And remember, we're looking at 20 milligrams per liter for EPA guidance. So an order of magnitude at least higher in extreme cases. And this is all draining to a drinking water reservoir. Next slide. And in fact, we can trace that. We really think most of that is a de-icer signal. On the very left here, you're seeing sodium ion concentrations at kind of the worst offending site at Cub Run, which drains to Bull Run. It's a fairly developed watershed. And these are actual measurements of sodium concentration over time. And we've colored them by the water temperatures. So blue is cold, it's in the winter. And you can see these peaks, routinely show up in the wintertime, but there's a lot of year-to-year variability. And I've highlighted two major events, event E1 and E2 there, where you're getting concentrations above 200 milligrams per liter. And not that all of this sodium is coming from Cub Run. Obviously, there's de-icers being applied all throughout the watershed, but we can see those two events washing into the Griffith Water Treatment Plant intake, event E1 and E2 in the middle graph, and then finally basically passing through the water treatment plant and into the finished drinking water. And so basically, we can see a cause and effect relationship between de-icer application and then what's coming out of your tap in your home. Next slide. This kind of leaves us with, well, what are those possible solutions? Coming back to Carl Berger's beautiful vision for us. And we're working on this right now, but starting at the top, obviously, de-icer wash-off is a huge issue. And, luckily, the Virginia Department of Environmental Quality had formed a consortia called the Salt Management Strategy, SAMS, which is basically great guidance on how combination of interventions in terms of the application of de-icers and also potentially smart stormwater infrastructure and so on could be utilized to try to minimize the de-icer signal. I think that's a really obvious place to start. Our project also indicates on the left there that we should start thinking about reducing sodium inputs to the sewage collection systems as well, from industry, from households, water and wastewater treatment. And there's really great opportunities for product switching that we could potentially affect through social marketing. And then, on the water treatment side, on the lower right there, we can start thinking about ways to reduce sodium inputs from water treatment. And, in the UOSA case, we're kind of exploring precisely how that works. A big part of that was trying to figure out exactly why they were having to add so much sodium hydroxide. And again, it ties back partly to coagulants and sort of treatment of acidity generated within the water treatment plant itself, but also 50% of it is coming from the, essentially neutralizing acidity in the reservoir, which really suggests this is a big social ecological system that you have to kind of consider as a whole. So anyway, that's it for me. I think next step we have John Jastram talking about what the USGS has learned from all of their monitoring data. And John, over to you.
Great, thanks, Stan, and thanks to Sujay and Steve for the introductions earlier. So I'm John Jastram with the U.S. Geological Survey, and I'm going to share with you today some of the work that we've been doing based on our monitoring data for urban and suburban streams. This is work that's largely been done in Fairfax County, Virginia, as part of a monitoring program that we operate cooperatively with Fairfax County. And I want to highlight that much of the work I'm presenting is actually that of folks on my team. So Aaron Porter, Jeff Chanett, and Jimmy Weber deserve the credit for what I'll present today. So we have this wonderful monitoring network throughout the urban suburban landscape of Fairfax County that currently consists of 21 stream monitoring stations on small urban suburban streams that have watersheds of about a half square mile up to 5.5 square miles. So really relatively small watersheds. We're doing a lot of work. Oh, I'm sorry. We can go back to that slide. We're doing a lot of work at these locations, very comprehensive monitoring effort that includes various hydrologic measurements, so stream gauges, water quality measurements that include discrete sampling and continuous monitoring, and ecological monitoring that includes benthic macroinvertebrate, fish communities, habitat, and so on. Much of the program is focused on nutrients and sediments, but we do have aspects of the work that inform our interests in stream salinization. In particular, we measure specific conductants along with all of our discrete water quality samples, and we have continuous monitors, instruments that are deployed in the streams measuring specific conductants continuously at 6 locations. We also have a limited amount of major ion sampling that includes chloride at 6 of these locations that we've been doing since 2020. So we have a lot of work, a lot of data to inform various analyses of stream salinization. And so that's what I'll be sharing in the next several slides. So we can jump to the next slide. So from our work and from other work, we know that specific conductants and by proxy salinity and chloride concentrations are positively correlated to watershed imperviousness. So this is largely because of the road coverage. And we know that SC is a strong surrogate for chloride concentration. With the data we have, we can look at how those conductance values vary across different hydrologic conditions and across different seasons. And what we see here is that during the warm season, those April through September months, when we're not applying de-icers on the landscape, we generally see a dilution pattern when we have runoff occurring. So that rainfall that's running off is not adding salinity to the streams. But we see very different patterns in those cool weather months or winter months, where we do occasionally have that wintry precipitation that results in de-icer application. We see that enrichment of specific conductants and chloride in our streams. Next slide. And so we can look at that over time. We've been monitoring these streams since 2008. And so we conducted a 10-year trend analysis several years ago to look at how specific conductance changed over that 10-year period. And what we see is widespread increases and relatively large increases in specific conductance across the entirety of our monitoring network over that period. And we see that those increases tend to be higher in areas with greater imperviousness, as indicated by the red shading on the map. Next slide. Oh, we could probably click 1 or 2 or 3 times. We'll get there. All right, so we wanted to update that trend analysis, add a few more recent years. And it just so happened that these recent 5 years, we have had noticeably less snowfall, less wintry precipitation in that period than we did that initial period. So it really set up an interesting opportunity to evaluate, how directly that precipitation influences salinization of our streams. Next slide. And what we see is that, in fact, there is, some change to those trends over time. We don't see quite as strong increasing trends across the county as we did initially. We do still see those increasing trends, but they're muted in some instances because of that lack of wintry precipitation in recent years. But interestingly, we notice a differentiation between our different physiographic provinces. So physiographic provinces are informed by geology and therefore soil conditions. And what we see is that throughout the Piedmont, we do have widespread significant increases in salinization continuing, while that dropped off in other physiographic provinces. And so we have a hypothesis that may relate to storage of chloride and in the soils in the system, and we'll talk about that more in a few slides. Next. So as I mentioned, we're collecting a lot of different types of data, and that gives us opportunities to really beat these data up in many different ways and really try to gain the best understanding of what's going on that we can. So this slide is just highlighting that we have continuous data in addition to those discrete data that really give us a lot of detail, and it really help us to get a detailed understanding of how the salinization is occurring within these watersheds. And it also provides some insight into some interesting patterns, such as the pattern we see on Long Branch here on the right-hand side of this slide, and we'll see that as well in the next slide. So we can also look at changes in conductance across the range of conductance values. So basically we could say, are the lower values of conductivity changing over time? Are the median values changing over time? Or are the high values changing over time? This helps us understand, the potential impacts of different mitigation programs and things like that. And what we see again on Long Branch here on that middle right plot is that there is a decrease in those highest values of specific conductance. So that leads to some hypotheses about, the potential response to decreasing de-icer application in that watershed as a result of management activities. So potentially some early signs of positive news there. Next slide. We can also look at how conductance and salinity are changing over time throughout the calendar year. So we might hypothesize that since de-icers are applied in the wintertime, we might see the greatest trends during those months. But actually during those winter months, we don't see many significant trends in conductance. It's actually in the warmer season months, spring and summer, that we're seeing the strongest indicators of increasing conductivity. And we believe this is because of salt being stored on the landscape in the watersheds, either in the soils or in shallow groundwater, and that making its way to the streams during those months or during those, or being a greater proportion of the flow during those drier times of year. So very interesting patterns that we're seeing during times outside of the de-icer application window. Next slide. And if we could click 2 or 3 more times here. One more. Thank you. So we really want to understand, what is it that's driving these differences between the watersheds and these patterns that we're seeing over time. So Jimmy Weber and others conducted some analysis here that was published in 2023 and found that the variability in our trends over time and conductivity can really be explained by three primary factors. And those were developed land, so basically that impervious cover that we talked about earlier, soil depth, so SC values are higher in watersheds with more shallow soils, so that suggests that those shallow soils aren't able to retain SC or the salinity, and it's making its way to the streams more quickly. And then air temperature, so that's our indicator of weather conditions. So obviously, years where we have colder weather, more wintertime precipitation, we're going to see greater salinization transport to the streams. Next slide. And so finally, we're doing some new modeling work to answer additional questions about stream salinization. And so we've developed this conceptual model that Jeff Chanit is working to calibrate and build out. That's really going to help us answer some key questions about salinization. It'll help us understand better how much chloride is being exported from these watersheds. We'll be able to back out some information about how much salt has been applied to these watersheds, which will be really critical information. That's a much more difficult number to get a hold of than one might expect. But we hope through this modeling process to be able to back out some of those values. We'll gain a better understanding of how much chloride is stored in watersheds that we're looking at. And then finally, one of the really interesting things is using this modeling approach, we'll be able to run some scenarios to get some information about what types of changes we might expect in the streams as we make different changes to salt application on the landscape. So how long might it take for us to see those responses in the stream, and what the magnitude of those responses might be if we were to implement different management practices. Next slide. So to wrap it up, I think all of this information is very useful to many different stakeholders, as it's been made clear, hopefully throughout this session today. Stream salinization is a growing concern, particularly in our urban and suburban watersheds. And the monitoring that we're doing at USGS and the work that our collaborators at Virginia Tech and University of Maryland are doing, really generating useful information to help us understand this problem and develop management responses to it. So the monitoring helps us understand better where these issues are occurring, whether they're getting better or worse, and whether or not, which watersheds are at greater risk than others. It's also very useful for tracking progress towards meeting regulatory requirements, such as TMDLs. As we discussed on the last slide, we can build scenarios and forecast predicted changes as a result to management practices that may be implemented. And it's also very informative to better understanding causes of stream impairment as a probable stressor for aquatic life. And so with that, I will hand it back to Steve, and I think we'll have time for questions for Sujay, Stan, and myself. So thank you.
Yeah, great. We appreciate the great presentations. We've had a few questions in the chat, some of which have been entered in the chat or answered in the chat, but one I saw from Renee Barrasso with ICPRB, I think for you, Stan, is what kind of seasonal variability you see in the salt loading in the Occoquan?
Yeah, there's very strong seasonal variability because of that ternary diagram, that showed the day-to-day flow being so strongly driven by weather conditions. And so what we see is that toward the end of the summer, probably due to a combination of evapotranspiration within the watershed as well as decreased rainfall, the input from the watershed slows or reduces, and then the contribution of the water reclamation facility, UOSA, goes up. And so we actually have a model that tells us what the fraction of UOSA's effluent is at the Fairfax Water Griffith intake, and we can see that climbing for most years, right? There's a lot of year-to-year variability, but most years we can see that fraction climbing throughout the summer, peaking in the fall, and then essentially dropping quite suddenly, during some major rain events at the beginning of the winter. The other thing that's happening, of course, is the reservoir stratifies in the summer. It's monomictic. and we have a lot of acidity being generated in the hypolimnion, and actually the water also has high alkalinity, and the combination, which is weird, but the combination of the high acidity and the buffering is such that Fairfax water overcomes that by adding essentially an elephant's worth of sodium hydroxide, on a daily basis to basically neutralize that acidity. So tremendous seasonal processes going on. And then the question is, can we even think about manipulating the ecology of the reservoir to try to minimize this acidity issue, or even where we draw the water in the water column is something that we're talking about. But yeah, the answer to your question is absolutely tremendous seasonal variability, both from the watersheds, from the water reclamation plant, and then also what Fairfax Water has to add due to acidity neutralization.
Great, appreciate it. I know we've had a couple other questions in the chat, which I think have been answered there, but I do have one maybe for each of you, which is, we've been working on this problem for a few years now. Sujay, in your case, a long time. It can be easy to think of like doom and gloom, like, oh, hey, we have, urbanization and population increasing all the time. Things are just going to keep getting worse. But I wonder if you have a takeaway for everyone that was here in the session today, whether it's either hope for the future, or maybe something unexpected that you learned in doing the research we've been doing over the last couple of years that either was counterintuitive or when going into it, you would not have expected to see. And maybe we can start with you, Sujay, and then just go in the order of our presenters. So Stan and then John.
Well, I think that, that there's potential for recovery, like John was just showing in the last presentation. It's important to know that different physiographic provinces might respond differently, or there's vulnerability, but there is a chance of recovery over time. What surprised us, I guess, is that when we were monitoring longitudinally, and just the importance of conservation, and there's a lot of money spent on restoration and with stormwater management, but conservation of urban parks and expanding those can make a difference in terms of water quality. It's just that the extent of conservation that's needed doesn't always, we just kind of, it's kind of like a death by 1,000 cuts. So conserving those forested areas in urban areas, don't give up on them, because they do make a difference. Maybe at a small scale, but things add up.
You're on mute, Stan. Hang on, you're on mute.
Sorry about that. Coming back to Carl Berger's beautiful vision for us, I think that at least in this one water system that we've been focused on, the Occoquan system, it all comes down to trying to understand those sources, their seasonal variability, their day-to-day variability, and then developing from that interventions that could potentially make a huge difference. And I think you're really talking about innovations in the stormwater side, in terms of maybe trying to capture some of that really salty runoff during de-icer events, which are quite limited in our area, so wouldn't necessarily be a problem to do that. Thinking about the one water aspect of it, that everything we put down our drain ultimately ends up in our drinking water supply. There's not any reverse osmosis for the wastewater treatment, so that all goes right on through. And so thinking about product switching, I noticed there was a question in the chat about which laundry detergent you should be using. We found that the powder detergents are extraordinarily high in sodium, so moving to a liquid detergent. And we'll have more on this, because we're actually working on a research article right now to describe in more detail. But the bottom line is, absolutely, I think that there's a lot of different ways that that we can address this problem, at least in a one water system like the Occoquan, and it all starts by understanding what's driving it.
Yeah, no, thanks, Stan. I'll just kind of echo what Sujay was saying. I do think there is some hope. We're starting to see some glimpses of that, I think, in some of our monitoring data. I noted that the trends that we're seeing have depressed in recent years. We did have less snowfall, less winter precip during those years than we did earlier in our study. But I also know that there's been a lot of work by COG and local governments to inform the public about this issue. And, you know, whenever there's wintertime precip, I see social media campaigns about applying less salt and things like that. And so hopefully we get a big snowy winter and people put down less salt, and we can show that really is helping things. And also, you know, I'd say we at USGS monitor a lot of urban watersheds, not just those in Northern Virginia. And we see in other places where, you know, salinization is of lesser magnitude. And so I think that relates to climate conditions, but also just application patterns and things like that. So I do think it's something that we can turn the tide on and look forward to seeing that in our monitoring data.
Great. So I want to thank you all for great presentations today. We're right at noon, and I know we need to wrap things up. Dylan, do you want to give folks a quick run on what's up next for the summit?
Yes, thank you, everyone. So thank you so much to our panelists and moderator today. It was a great session. And I just want to remind you all that next on the agenda is our lunch panel, two parts perspective on to 1 part equity, a conversation with Dar Williams and Russell Armstrong that starts at 12:15 p.m. Please join that session by returning to the main Zoom event lobby, and we will all join you there. But for right now, I will be closing out this session shortly. So thank you all again.